All right. Our second speaker for our summit today is Richard Williams. We welcome Richard. Richard has a 38-year history with Dow Corning Corporation prior to working with StatEase. He was emphasizing a global track record of product and process development and improvement. Richard is a Six Sigma Master Black Belt, and he has trained over 200 black belts around the world in those Six Sigma principles, including the use of design of experiments fundamentals to deliver business results. He also led and coached hundreds of projects in his tenure at Dow Corning. Using Six Sigma and DOE principles, Richard led the effort to create the world's first metallurgical grade solar silicon and created a manufacturing capability in Brazil to launch that product. Richard is a chemical engineer, and he specializes in the use of statistical methods to support product and process development, improvement, and control, most notably the use of DOE and statistical process control. Richard's business training and experience bring a business-driven focus to the effective use of statistical tools. So with that, I would like to welcome Richard to our 2023 DOE Summit.
Well, thank you, Sherry. I had almost forgotten some of those details, and it's refreshing to hear them again. If it wasn't mentioned, my other claim to fame is I frequently conduct training under Sherry's leadership, conduct training for StatEase. So I'm pleased to be here today to talk about what really turned out to be a very fun project, resolving a quality issue with a client for computer chips with a product that my client was manufacturing. So this was a fun little project, and it took a lot of encouraging to get people to accept the idea that a DOE was going to be the way to go on this. So I'm happy to share this little exercise. I find it interesting that yesterday we started off with chocolate chip cookies using an advanced response surface method, a combined design, and we just heard the nuclear industry using an RSM design. So it's really impressive to me and really enjoyable to hear the different applications for designed experiments. So I'm going to bring you another one in the world of computer chips. So as Sherry mentioned, I guess I'll skate through this quickly, but I am a chemical engineer. Been, as Sherry mentioned, 38 years in the industry. And skipping down to the bottom, yes, I do teach courses and webinars with StatEase. So once again, I'm pleased to be here with you. So here's the situation. A computer company, specifically one that works with computer chips and prepares them for assembly onto circuit boards. This computer company, who I won't name, but you know who they are. That's all I'll just simply say. They had a third round of over a 3-year period of failures with the product that my client was manufacturing. That product is called the Thermal Management Interface, or TMI. And the TMI material, which my client manufactures, was producing bubbles, okay? And I'll get into a slide in a moment to explain more completely why that's a bad thing, but suffice it to say, this is the third round of this problem over a 3-year period. That, you know, the first time that it happened, a team went out there and allegedly solved the problem. A year later, it happened again. And this third time now, you know, the computer company is getting a bit more alarmed. So the prior root cause efforts failed to resolve this sporadic bubbling issue. Okay. So the TMI manufacturer, my client, was faced with the need to, you know, immediately resolve this, and now it's under the threat of losing the business. It's gotten to that point now. And this was a substantially, you know, it was a very profitable business to be in. So that was not exactly a desirable outcome. So a team was quickly pulled together, and given the 2 root cause analysis failures that had happened up until now. They wanted to bring somebody into the story that was kind of neutral and new to the story, and could provide some leadership. My Six Sigma experience was helpful to that, and a sense of independence. So I could kind of referee the feuding parties as well as provide some leadership to try to get the thing resolved. The computer company did not want to be heavily burdened with time-consuming participation in correcting the issue. They felt it was my client's problem to resolve, and they really didn't want to get terribly involved. Just go fix it, bring it back, and make sure that it'll never happen again was kind of the message. Let me pause there and explain the level of interest that the computer company had on this topic. So when I was brought in, and together with my team went out to their manufacturing location, they ushered us into not a conference room, but kind of a small size auditorium with somewhere between 30 and 50 people in it, which already was a bit alarming. Turns out 2 of the people in the room were vice presidents of the company. Now they have our attention, and they reminded us that this problem had happened twice before, and that it's causing them to scrap hundreds of very high-priced, high-end computer chips, and that this problem needs to be resolved once and for all right now. And by the way, it's your problem, not ours, so don't include us in your activities. Okay, so now I'm really glad I was invited to play. So here we go. So we're looking in this example of using a DOE for the purposes of root cause analysis or root cause investigation. That's really what this came to. Really, when you have a problem of consequence, and incomplete knowledge, you're going to need some new information, and that's going to have to come to us through some form of experimentation. You can look at existing data. You can do fishbone analysis, which we did. You can look at SPC, statistical process control, for the parameters that you're tracking. All of that is helpful, but if you're really going to build new knowledge, you're going to have to do some kind of validation. You're going to have to do some experimentation, some trials. What's really important is root cause analysis relies on establishing causation, not merely correlation. So we really needed to dig in and understand the true root cause and then go remedy it. I think Steve yesterday in his presentation, spoke some words that were near and dear to my heart. As a Six Sigma guy, he mentioned that the use of the DMAIC process is very, very important when it comes to problem resolution. So for those that aren't familiar, DMAIC is define, measure, analyze, improve, and control. And that's the world that we found ourselves in with my client. Is we had to define the opportunity, measure the performance, analyze the data, and make sense of it all, figure out how to improve it, and eventually satisfy the computer company that we in fact had a control strategy that was going to solve the problem. So the need for new knowledge plus budget constraints is really the domain of DOE. We've heard that multiple times throughout this seminar, is that you get the maximum benefit with the minimal work through using a DOE, and you get statistically valid conclusions, and you can create sustainable solutions. I think many of us have observed that those of us on the inside know that to be true. Those of us that are not familiar with DOE look at 30 some runs or something like that and reach the conclusion that well, that's just way too costly, we would never do that. Well, what's the cost of not understanding your product and its attributes and leading to quality issues, right? So a lot of times there's plenty of time to go fix it, but not always enough time to go do it right the first time, right? So anyway, I digress. So here's the situation. We have bubbles in the thermal interface. So on the right-hand side, there is a little, let's get a pen here. I just use a laser pointer. We have the computer chip referred to as the die. So that's the bottom layer. And what's happening is there is a lid being placed on top of the computer chip. And in between the two, there is a thermally conductive material called the TMI, the thermal management interface. And the goal of that is to help this whole assembly transmit heat through the lid, right? So we want a good thermally conductive material in the middle here. So you can see we're talking about, some form of computer chip. And what the customer was observing when they would, from the top now, take a look at this, an X-ray, if you will, of this whole assembly, is that on occasion they would have, a bunch of bubbles in the thermal management interface layer. And they were able to kind of characterize it to say that when it's like on the left-hand side, that's a disaster for us, and that causes us to scrap the chips. But on the right-hand side, which they measure as 2% voids or bubbles, that would be an acceptable tolerance. But when it looks like the one on the left, and you have bubbles throughout this thing, you're creating all kinds of problems. Specifically, this material contains a metallic flake that's used in a matrix, and the metallic flake is used to conduct the heat. And okay, if you have a lot of bubbles in there, well, a material with lots of bubbles in it is sometimes referred to as an insulator, and that's an undesirable phenomenon. Plus, it doesn't adhere the lid very well to the computer chip. So all kinds of problems when you have this bubbling take place. The thermal management interface is packaged in syringes like that, and then that goes to the assembly line at the client, and then they put or at the customer, and they put the material onto the computer chip. And but just casually mention at this point that the thermal management interface is a curable matrix, means that it'll, under the proper conditions, it'll form a solid material, but it contains 80 to 90% of this thermally conductive metallic filler. So it's, the majority of the formulation is this metallic filler. So let's see. Okay, so the first point I want to make is it turns out that in spec, okay, so as produced by my client, the in spec material can perform, good or bad at the clients. So here's the story, right? So we saw this picture before on a previous slide, and here's kind of if they pry the lid off it and just take a picture of what the computer chip and the lid look like, you can see that it's just laced with these bubbles, these voids. Okay, so that's a true statement. So the computer company tells us that, look, here's a known good batch and a known bad batch, right? One that worked well for them and one that didn't. Can you evaluate and confirm whether or not they perform? Well, so sort of brainstormed with the team and came up with a way to approximate their application, and it was a very simple test. We took microscope slides and put the thermal management interface material between the microscope slides and cranked them down so it was the proper thickness. And then we ran it through the heat cycle as prescribed by the computer manufacturer, do it exactly like they did it. Well, as it turns out, the known bad batch, well, we got a bunch of voids in it too. Looks just like their lid, right? I mean, so our slides, microscope slide test was a pretty good indication of what was going on. And by the way, the known good batch was, well, it was perfect. We didn't see a single bubble in it. So basically, at this point, we're able to say that that we were able to replicate the problem, and therefore the customer is, let's say, off the hook, right? That the material is specific to the product that my customer was, or my client was manufacturing. And despite despite the fact that all of the materials were in spec, some perform and some don't. So we have something going on that we clearly don't understand. So we did, like Steve talked about yesterday, we sat down with the team and did brainstorming. We involved the client, well, the computer company with this as well. So we sort of went all the way around the tables. This one's laid out a little different than Steve's yesterday, but we looked at the fundamental manufacturing steps. We looked at the raw materials, which include, my client produced the matrix, the material that would cure under the heating cycle. And then there's an external metallic flake that goes into the product at 80 or 90%. And so we had that raw material. The processing involves a mixing and pre-packaging. The packaging itself, there's into the syringes, there's a de-airing process, and then they load the syringes. And then the customer, uses the syringes in their application. The material is exposed in their environment for a period of time, and then it's heat cured once they put the lids on it, right? So they batch them up and then put them into an oven and go through this particular cycle. So we looked at these steps and we imagined, well, what could go wrong in each of them? And the processing. Well, you could load, mixing, pre-packaging, and could we envision anything in there that might be a problem? Well, if it's poorly mixed, I don't know. So we'll call it a yellow flag, that there was some things going on there. The packaging itself, there's a de-air step, and that really was the focus of the prior 2 rounds of problem solving, right? Well, there's bubbles in the product, there must be air trapped in it, and we got to do a better job of de-airing when we package the product. Well, so they improve that process, put it under control, and we still have sporadic problems with the client. So something weird is going on that we don't understand. The customer application, well, we're going to give that a green check mark here because we were able to produce the problem at, my clients, the microscope slides that I just showed you before. So that isn't completely it. That said, there was a relevant factor that the computer company felt should be included in any study. They wanted to find out if that was going to contribute to the matter. And so we'll eventually see that works its way into the design experiment. Now we get into the raw material question. And now we have to dig into understanding my client's material a bit better. And so we bring the process experts together. The same process experts that insisted that it was all about de-airing, well, now we're gonna dig a little deeper. Okay, so now we're gonna use some real root cause analysis approaches to kind of sort out, well, one of my favorite root cause tools, a very simple one, is identify where the problem is and also where the problem is not. Where might you expect to see this phenomenon but don't? Well, it turns out that they make a series of these products, and it's only this particular product that is having an issue. Okay, so there's lots of TMI materials being produced using different metallic fillers, but this particular one was meant to be a high-performing product. And I won't tell you exactly what the metallic filler is, but let's suffice it to say that this particular product is the only one to use this particular filler. And 80 to 90% of this material is shipped to this particular computer company. So I'm beginning to suspect now, and the matrix is used in all the other products, so we're beginning to suspect that there might be something unique about this metallic filter that's lending itself to the problem. Okay, so now we're starting to, okay, that didn't build like I anticipated, but we'll get there. I'm going to put it all in here. I thought I got rid of the builds, but here we go. So now we're starting to dig into the reports and understand the technology a little bit more, and we're trying to figure out what could cause these bubbles in the thermal management interface. Well, it turns out that if there's some moisture around, this is the theory now, that the chemistry of the matrix material in the presence of a base catalyst would liberate hydrogen gas. So that is a known phenomenon in the literature at my clients. Okay, so that could happen. So then we take a look at several batches at the customer, the computer customer now, that succeeded or failed. And we measured the amount of water in the product. Well, it turns out that there is something of a very loose correlation between the water amount and the bubbles that were indicated by the computer company. Okay, so there's at least something of a correlation there. Okay, not gonna claim causation yet, but there certainly is an indication that maybe this theory, pardon the pun, holds water. Then we went out to the metal flake producer and had a conversation with them. Do you guys ever have any basic contaminants in your product? And they sort of laughed and they said, we have base all around our shop. It's a common material, and we had no awareness that might be of concern to you. Oh, well, that's interesting. Do you think you could get rid of it if you needed to? Oh yeah, that would be easy. Okay, well, fine. So now what we did is we identified that moisture and this base catalyst could potentially be present in the filler, and if so, we might be liberating hydrogen gas. Right. So now we envisioned a 3-variable DOE to validate root cause. So the water, the base, and the customer had a process factor that was also linked to the phenomenon, or potentially could be. So they wanted that included in any eventual studies. So we went to the metal flake manufacturer and said, could you make us, do you think you could set up to make these 4 corner materials for us? Do you think you could, within this range of water that we specified in the catalyst level, the base catalyst level, do you think you could execute your process to kind of target those 4? And then our goal was, well, we would blend the orange points with a bunch of center points. We'd blend those in order to to round out a DOE, if you will, but to get them to make 4 was already pretty good. So they agreed to give that a shot. And instead of this nice little window like that, they ended up producing something like this. I mean, so in the real world, you're going to get what you get. So they made these 4, the silver ones now, they made those 4 materials. And then we were able to envision, just with the quantity provided, we were able to envision making the orange points as, So, okay, so now we got to figure out how to work that into a designed experiment. So the first thing that we did, recall now that the computer company really didn't want to play too much. They didn't want to be terribly involved in this thing. They just wanted us to prove that we understood the phenomenon and could resolve it. So what we did is we went out and did a lab DOE as a preliminary effort to prove the concept. Okay, so we didn't involve the customer. So we didn't include the process factor that the computer company wanted us to include because, well, that was their process, not ours. So we really did a 2-factor central composite kind of, but we input the imperfect, right? The points that I just showed you weren't going to be an exact central composite design because the corners weren't where we want them. So we just used a central composite model and just put the points in as we had them. Okay. We made the lab blends of the 4 fillers, created the axial and center points as best we could. It turns out that an optimal design would have been a better choice, taking into consideration the skewed design space. Nevertheless, we just kind of threw it in there and tried to see what the software would tell us. And there will be a second round of DOE that involve the customer, and we're going to be a little more careful designing that one. So sometimes a picture is worth 1,000 words. We gather all kinds of statistics and make sense of the story. But this was already compelling that perhaps we were onto something, right? We look at the base catalyst, we look at the amount of water in the system, and it looks like you have a yes and, right? That the more base, the worse, especially in the presence of water, that if you have sufficient catalyst and the reactants are present, then you get the liberation of hydrogen gas as theorized. So that that made short work of this. And we are able to kind of go out to the client now, the customer, I should say, and show them this chart that said, look, water, and catalyst, your goal is to have less than 2%, right? So we have that. And there's this big blue region where we're underneath that 2%, and there's a place where we can make really bad product, and we know that we can do it. The pictures, again, are worth 1,000 words. Okay, so at this point, we've defined the problem, and we've measured performance, right? We understand that the problem is bubbles, and we set a specification of 2% would be acceptable, 2% voids according to the computer customer. We've measured the performance. We know where we stand right now, and we're in the middle of this analyze phase now in the DMAIC process for Six Sigma. The problem with that design that we created in the lab, of course, is that with the skewed distribution of points, we have the standard error plots really kind of fade off when you get outside the region that's cropped in by the where we were collecting data, right? We don't want to extrapolate. So the standard error of the design looks really weak up in the corners where you can see the red points are where we had data. And when you get too far away from the bulk of your data, the ability to make predictions fades quickly. So that's something we're going to want to fix in the next round of studies. So now we got back in the airplane and went off to the computer manufacturer. By the way, this was a lot of frequent flyer points on this one. The computer company wanted us there every 2 weeks for an update in person. Okay, so they want to make this as painful as possible. We get that. They're sharing the pain for us. So every 2 weeks we're out there. So they're somewhere in the U.S. Let's just say that. The metallic flake producer is in Massachusetts, so we're up there. The manufacturer, my client's manufacturing operation that produced this product and put it in the syringes was in Japan. So there was plenty of travel going on to pull this thing off. So anyway, now we're back to the computer manufacturer, and we're able to show them now what the lab study revealed. Okay, and we invited them to participate into a second round of designed experiments, which they were less than thrilled. If you recall, they didn't want to play at all. So we had to entice them. We had to show them. So first of all, by demonstrating what the earlier DOE was able to reveal, that drew them in, right? They were not practitioners of design of experiments and were leery of the concept. We had to do a little bit of training to get them on board. But the DOE for the second round would be a full-scale replicate of the lab DOE, but would also add the customer's process factor that they wanted to study, performed on their shop floor. So they didn't want to be involved, but they wanted their factor included, but the only place that factor could be included would be on their shop floor. Also, we were going to collect actual void data, not what we sort of approximated in the lab, right? So we're gonna do this in situ in their environment, so that we can design a product that will work specifically in their application, right? So and the goal here is we're going to validate the filler specifications that would give acceptable TMI performance, right, in their process. So basically, from our lab work, we had a validated root cause, and the next step now is we want to gather sufficient information to set the specifications required with our metallic flake material, so that it would perform specifically in our customer's application, including their process factor. So an optimal RSM was designed, and that's going to allow us to use the constraint tool to crop the design space. So in a moment, I'm actually going to open the software and build this with you and show you what we did. The DOE was essentially a 3-factor study, but really it was kind of laid out as a 2-factor study with each resulting run evaluated under 3 process factor settings, right? So I really like what Mark had to say yesterday, kind of loosely interpreting a quote he had from Box, and that's that, you know, really what you want to do is you want to block what you can and randomize what you can't. More specifically, Mark included the idea that, you know, split plots are kind of a more sophisticated way of blocking sometimes. So we want to include that thought. But if necessary, regardless, proceed in whatever run order you must rather than abandoning DOE. So that's kind of the zone that we're in. We're going to have to do two factors, kind of lay out the study that way with the material that we have available to us, right? I can't just get any formulation I want. And then we're going to evaluate those under 3 process vector settings at the customer. I don't know why we settled on 6 center points, but I'm glad we did. It was a pretty robust way to prove that this thing would be repeatable. Right, so we ended up doing a 42 run design, but that includes the 4 factorial points, 4 axial points, and 6 center points. Okay, so that's what, 14, and then each would be evaluated at 3 process. So there's really 14 specific, you know, canisters of material that was sent to the computer manufacturer. And it was done blind. The client didn't know, or the computer manufacturer didn't know what was what. We just sent them these 14 materials. So what we did is we kind of laid this out, knowing the material we could produce from the metallic flake. We knew what material we could produce by blending what we had, and so we created the you know, the water and catalyst levels were kind of dictated by what we had, and then we're going to evaluate each one with the 3 different process settings, right? So we have all these different runs up to 42. Okay, so that was how we're going to have to do this. And so let me go to the software and show it how we accommodated this situation. So let me try to open this up, and hopefully, I believe you'll be able to see the software, I believe. Yes. No, let me get there again. Okay, and if I'm getting there. Pardon the tech. Okay. Now I think we're getting there. Okay. So what we're doing now is we're creating an optimal design. And the reason we're doing optimal is because I want to crop the design space to get rid of those regions where the standard error was too high. Specifically, the computer manufacturer insisted that we wouldn't do any extrapolation into those regions. So I wanted the design space to be cropped. I can't do that in the central composite design. So what we're going to do is I'm going to use this edit constraint feature in the optimal, so I can create an odd-shaped design space. And we're going to use the add constraint tool, and we're going to cut off the corners so it matches what we need. Well, the first vertex that I need to play with is this first one, and the constraint point here is going to be 0.01. You'll see later how this works. The second one is 5, and then the factor C, the process factor, I don't need to do anything with that, so we can skip that. And that builds the constraint to cut off one of the 2 corners, and then we'll do another one. This one now, the vertice of interest will be 0 and 44, and now A has to be greater than 0.01, and that's 14 here. So we're a little algebra and a little math to kind of sort out what those values need to be. But in the end, what we're doing now is we've created these constraints. Now I knew that I was going to do 42 runs, so here's what I did. When we go to the next screen, this is the optimal custom build, and it's requesting, you know, 20 runs, which include 10 model points for a quadratic model, 5 like a fit, 5 replicates. But I'm going to kick this up to, I'm going to put an additional 22 model points to kick this up to 42. Now I realize that I'm not going to end up using the specifically requested points that the optimal will create for me, but I'll show you what we're going to do with this just the same. So we had the voids or bubbles, and we'll finish the design. So here's my 42 run design with all these specific conditions that we probably won't run. but I want to evaluate this one. So I'm going to come over here to evaluation. We'll look at graphs. And the first thing I'm going to do, we'll come back to this one for a moment, but I want to look at the contour plot. And we see that now I have successfully cut the corners off of my design space by using the constraint tool. So now I'm working only in the region of interest. These isobars kind of tell me a little bit about the standard error plot, so it doesn't look too bad. I always like to look at the 3D surface of that. And you can see that that's kind of, you know, I'll say low and flat, right? It's kind of low and flat. Well, this all is translated into the fraction of design space. And, you know, I don't have relevant specific information to put in here, but I'm going to evaluate this at what is probably a pretty robust 1-to-1 ratio, just as a benchmark. And if I do that, I see that fraction of design space where I can make suitable predictions is 99%. So that's, you know, that's stellar. That's regarded as really, really solid. Now, however, I'm going to put in the design points, not the optimal ones, but the ones I'm forced to run, right? Mark's quote from yesterday, do what you can, but in the end, run what you can, run what you must. So let's take a look at that. And I'm just going to do a quick copy paste here from a spreadsheet. So now what we're going to do is I'm going to replace all that with what we can do. Okay, so there it is. So there's the runs that we're forced to run. Now let's evaluate it. Not as flat. Okay, so that's going to be interesting. The contour plot, however, you know, I still see the data points where I want to run. These isobars are kind of what they are. If I look at the 3D surface on that, you know, the optimal was better, but this isn't terrible. You know, I think we're gonna say that this looks pretty good, but let's validate it with the same benchmark in the FDS graph. And here we see that we're up to 86 as compared to 99. So yeah, the optimal design beat my manual design, that's for sure. But this seems, you know, it's greater than 80, our, you know, rule of thumb. So we're gonna go ahead and do this one. So we went out there, collected the data, and because Thaddeus taught me how, I will load an existing simulation. And there's the data. Okay. Now, now we're going to analyze it as usual. And we'll start the analysis. And what I didn't tell you before is it looked as though a log transformation from the lab run was going to be helpful. So here we're looking at this, it's suggesting a quadratic. It's indicating that cubic might bring us a little extra value. But let's quickly run through this. The ANOVA analysis here, perhaps I could do a little model reduction, but the ANOVA analysis is telling me that I do have significant lack of fit. And if I look at the diagnostics, that indeed, just like the lab study, the box Cox down here is recommending that I do a data transformation, specifically a log. All right, so we're going to redo this analysis. And I'm going to call this one, I'll keep them both so we can compare if we need to. I'm going to call this one with the log. And here I'm going to use natural log because that seems to be a more logical fit with the phenomenon that we're seeing. Turns out, without making too much noise about it, this K was going to be required to stop us from taking a log of 0 and blowing up the thing. So anyway, we'll start the analysis. And, you know, now it looks like a quadratic is going to fit pretty well. I don't get a lot of additional benefit by even going up to cubic, so that's a good thing. We look at the model. We can take a look at the ANOVA here. I do have some terms that maybe can come out like C squared. So I'm looking at the predicted R squared of 0.74. So I'm going to try model reduction. I'll use the automated approach to pull some terms out. I use p-value backwards in this case. I get the same result no matter which one I use. The C squared drops out, but I do have A squared and B squared. So the process factor is contributing, but it's only a linear effect, whereas I have some quadratic behavior for the two factors that we're looking at. I improve the fit statistics by doing model reduction. Significant model, not a significant lack of fit. Make a long story short, the diagnostics now look pretty solid. And we can go to the model graphs. We can look at the contour. Maybe I'll add the contour now for the, let's change that value to set contour value to 2% where the customer needs it to be. And we can see now that we have a region where we're going to be successful. And I can change the process value. So their process factor definitely is having an impact. I like to look at this perturbation plot sometimes. This is going to, and I'm going to change this to the in the transform scale because it seems to make a little bit more sense if I do that. So this is the log of the bubbles, if you will. And now I can see what happens as I change the process factor, that it exasperates the phenomenon for sure, okay? So as I drag the process factor from its low setting to its high setting, those two other curves just simply rise up, right? So it makes a bad situation worse. So it's a contributor, but it's a linear contributor. All right, so next we want to find out, well, okay, how about specifications? Now that we sort of validated this whole story, what are we going to do for specifications? Well, we're going to go into numeric optimization. I'll click on voids. What do we want to do with those? Well, we want to minimize them. The upper range here is going to be 2. And we can look at solutions, and sure, there's going to be solutions, but I think the more interesting thing is going to be, you know, the graphical optimization. So if we click on that now, and we see that the voids at 2% can be anywhere in there, and we can play with the process factor a little bit to see where that needs to be. But really what's going to be interesting now, we want to set specifications that will work in their application for every batch that we produce. Okay, so how do we get to that? Well, back in the criteria, we are going to turn on the tolerance interval. And this is going to look at where, with 95% confidence, where 99% of the individual batches should reside. And this is not behaving as anticipated. So let me just simply say that I fat fingered something in this demo. So what I'm going to do is quickly open up the real one. You know, it works in practice every single time. But if it's ever going to fail, it's going to fail in public. That's just the way these things tend to go. So quickly here. So this now should be the one that that works just fine. So in a better world, you would have seen a slide that looks just like this one. Okay, so I don't know what I did in the last one. Never fails if you're in public. Okay, so now we can play with the process factor. And what we can see is, you know, 99% of the batches with 95% confidence should reside within this bright yellow section of the graph. And now we can sort of pick the process factor and balance all of the considerations, also knowing what the metallic flake producer believes they can achieve. So putting all of these factors together, coming back into this presentation now, so we were able to set the specifications at, you know, 14 parts per million catalyst and a 0.01% water level, with the process factor more or less at the mid-range, which was completely acceptable to the computer manufacturer. Okay, so now we are successfully producing material with confidence using the tolerance interval to set specifications. And we have not only validated root cause now, but we've figured out how to improve the performance. We've worked with the metallic flake producer so they can control their process. We reset the specifications, and so we have a control strategy in place now to execute the discoveries that we gleaned from the DOE. So the takeaway messages are this. Number one, the quality is what the customer says it is. We either build quality into the product, or we kind of don't, right? So in this particular case, we ended up with a problem-solving exercise that distracted all of the product development people because they now had to give up their day jobs to come over and work on a problem resolution. We use the DMAIC Six Sigma process to solve the problem. There is another Six Sigma process called Design for Six Sigma, what I refer to as the emitted process, where we sort of go through up front now and figure out what's required to be successful. We would have done this DOE at the onset if we had gone with the emitted process, creating the material. But oftentimes we think we can go quickly to develop and launch a product, and then when it blows up in the field, we have problems to solve. But we get to pick which way we're going to go. But at the end of the day, the customer is the one who will decide whether the product works or doesn't work. And we can decide where we want to fit into that equation. DOEs are so incomplete specifications at product inception can lead to significant problems down the road. We didn't understand what was really important with the metallic filler. And even in our own internal reporting at my client, there was mention of the potential for this material to have, base catalyst in it, but we didn't understand the full importance of that and how consequential that could be. And oh, by the way, it was a random event at the metallic manufacturer that would that lead to the presence of this at this base catalyst. So it was, it wasn't going to happen every time, but when it did, it was going to be a problem. DOEs are fantastic tools to understand factors or mixture components, as Mark told us yesterday. So factors of importance, we can gather sufficient information to establish meaningful specifications. That's the beauty of tolerance intervals. Okay, so whether you call it design for Six Sigma or quality by design, the use of things like tolerance intervals helps us to find that spot where we can operate successfully, not just on average, but for every batch that we produce, right? Get the whole bell-shaped distribution into the inspect range. When we must, we can not only use DOE for product creation, but it is a very effective tool for root cause analysis, right? When it appears our product understanding at inception was lacking and new learnings are needed. And I was very pleased with Design Expert in being able to create the designs and to be able to communicate with the client and the eventual customer the findings in a very simple and straightforward way. The software, I believe, is simple but far from simplistic. It does a rigorous job and yet makes the communication in the real world for non-statisticians very practical and very simple. All right, that is my story. It was a fun it was a fun problem to solve, despite the threatening nature of my first meeting with two vice presidents in a crowded room. But I think everyone in the end was very satisfied with where it ended up. Last I checked in, there have been no bubble issues since this DOE was conducted and the results implemented. So with that, are there questions, Sherry?
Thank you, Richard. I've definitely had people ask previously, can DOE be used as a problem-solving tool? And you've just shown us a fabulous example of how it can. Yes, absolutely. It's a great problem-solving tool.
Well,
So,
that's interesting because at my former company, people would shy away from using it for that purpose, and and yet when I would do that, case after case, you would have meaningful results with what I think is minimal work. And yes, it can be, and it should be used as a root cause analysis or problem solving tool.
yeah, thank you. David asks if was the presence of hydrogen gas analyzed by the metal producer, your client, or the end use customer?
Yeah, so the end use customer never figured out on their own that it was hydrogen. Everybody at the onset was suspicious of more air trapped in it from the packaging step. So once we were creating this hypothesis that the moisture and base would liberate hydrogen, we took some of the bad material and I can't remember the details of the experiment, but we worked with our analytical people to figure out a test to figure out under these conditions when we heat it, would we liberate hydrogen into the head space of a test tube or something like that. And we did find that hydrogen was being liberated. So that was an early, it was kind of a crude, a little bit sloppy test, but sufficient to further the claim that in fact this chemistry can and does lead to hydrogen production.
Mm-hmm. Okay. At the end of this, did the metal producer end up using anything like SPC to help control their process or anything like that?
Well, we were certainly encouraged them to use SPC. I'm a strong advocate and champion of doing that, but I probably have had less success getting SPC planted in the world than I have DOE. But in the end, they agreed with simply that they knew how to attain the specifications we needed, and they would do the testing to make sure that the product passed the specifications based on the slide that I showed. And that's as far as we could take that. So we, if it doesn't pass our requirements, don't ship it. And that was a formal set of specifications that was set.
Okay, I'm not seeing any other questions. So, Richard, I'd like to thank you for participating in our summit. I love seeing, these real world examples and really hearing the story behind the scenes. It's just fascinating to see how design of experiments can be used. So thank you very much.